Hi everyone. So the videos were getting too long, and I actually cut out the part where I discussed varying forces. Um, so instead, we're going to go through two examples that are very similar to the examples in the homework set, where the force is not varying, it's just the force of gravity. But to compute the work required to do whatever process the problem is talking about, we need to think a little bit more. It's just a more complicated setup. So I'll discuss these two basic examples, um, and that'll be it for this video. Okay. So you have a 200-pound cable, which is 100 feet long, that hangs vertically from the top of a tall building. And we want to compute how much work is required to lift the cable to the top of the building. Okay. So here, basically, we just need to beat gravity. Again, gravity is what's holding this weight down, this cable down. Um, and to use the force here, because we're using British units, the force is basically given to you right here. The cable is 200 pounds. But notice different parts of the cable are going to travel different amounts, right? So, if, for example, if you look at a point uh, like this point right here in the bottom, when you pull the cable up, it's going to travel 100 feet, right? But if you look, for example, at a point right in the middle, it will only travel 50 feet, right? So each different point in the cable, you're going to need a different amount of work to pull it up, okay? And we need to take care of them separately. And so that's why we chop up the cable, just like we do when we compute an integral, chop it up like this, and then we compute how much work will just one interval require, and then we can just add all of them up. That will be the work required to pull the whole cable up. And so that's how we're going to start. We're going to say the work required here is going to be equal to the, well, I'll do a limit, right, to make these things become smaller. So n is the number of pieces. You sum from I equals 1 to n the work required to pull the ith interval here all the way up, right? So how to compute that work? Well, the thing that you need to realize is, well, we're basically just going to beat gravity, right? So there's going to be a force term, right? It's going to be force times displacement. Um, the displacement, if you're at a certain point, say that this is a point xi, then the displacement that this piece is going to have is exactly xi, right? So if you denote this by the coordinate x, the displacement is going to be x, right? So here it's going to be xi. That's the displacement. And what is the force? Well, you basically need to use this number here, 200 pounds, right? So the whole cable is 200 pounds. So we need to figure out how much does this tiny piece weigh, right? And so if the whole cable weighs 200 pounds, then a piece of size delta x will weigh 200 pounds, which means that, and it's 100 feet long, right? So it means that every foot weighs 2 pounds, right? So that's kind of like it's not, I shouldn't call it density because pounds is not mass, but it says how much a foot of this cable weight, right? So a cable that's 100 feet long weighs 200 pounds. So every foot weighs 2 pounds. And so delta x of a foot will weigh 2 times delta x pounds, right? 1 foot weighs 2 pounds. Delta x feet will weigh 2 delta x pounds, right? In particular, 100 feet will weigh 2 times 100, 200 pounds, right? So, and that's the force. So that the force of gravity will be negative 2 delta x on this interval, but we're going to beat it, right? So we use negative gravity is 2 delta x positive, right? And this turns into an integral. This is a Riemann sum. If you look at it again, this is the integral The xi's, they will run from 0 to 100. 2x, and the delta x turns into dx. Yeah. So this is, we're not using the formula integral of a force. You just have to think through the problem, and the integral naturally arises. And the thing that you should think about is that different pieces of the cable will travel different amounts. So every different piece will require a different amount of work. So you chop it up and you sum all the amounts of work needed for the different pieces. You make the pieces smaller and smaller. And if you focus in one piece, what is the amount of work needed? The displacement of a piece at place xi will be xi. That's the displacement that it needs to go to get to the top. And the force at that piece, we just used that this cable had 200 pound weighs 200 pounds and is 100 feet long, to know that every foot of this cable then will weigh 2 pounds, and so something of size delta x will weigh 2 times delta x pounds. And so that's the force. Used it positively to get the work required, right? And this limit turns to this integral, which is pretty easy to solve now. The antiderivative is, of course, x squared. You plug in x equals 100, x equals 0. That's just 10,000 pounds feet. Right? That's the unit of work. All right, so I have one more problem left for you. All right, so let's do this last example. We're gonna compute in this problem the work required to empty a tank of water by pumping the water out. Okay, so the problem says the tank has the shape of an inverted circular cone. So circular just means that the base of this cone is a circle, and it's inverted, it's upside down. With height 10 meters, so that's the height. Maybe we should start circling the values, but it's on the drawing as well. The height of 10 meters and a base radius of 4 meters. It is filled with water to a height of 8 meters. Okay. Find the work required to empty this tank by pumping all of the water to the top of the tank. And you can use it. The density of water is 1,000 kilos per meter cubic. We're also going to need to use the acceleration of gravity again, which is 9.8 meters per second squared. Okay, so I already drew a picture here for me to try to explain how we can compute the work necessary for these things. So we're going to try to pump all of the water up to the top of this tank. Okay, and want to compute what is the work required to empty all of the water out. Okay, so in the similar way, different particles, right, of water in this tank will have to travel a different distance to be pumped out of the tank, right? So if you're right on the top and you want to be pumped to the top, then you will only, at the top here, you're at this, look on the left here, I drew this x-axis. So if you're on the top, you're on this axis here, you're at x equals 2, right? So 0 is the top of the cone. The top of the water is 2, and all the way down the bottom is 10, right? So 0 to 10 is the whole cone. So for example, if you're right at the top, then you only need to travel a distance of 2 to leave the cone, right? While if you're in the middle here, you have a different distance that you need to travel. And if you're all the way down, if you're this particle of water right at the tip here, you need to travel 10 meters all the way up to the top, right? So a slice in there, all of the particles in one slice of water will have to travel the same distance as they are pumped up to the top, right? So what we can do is, again, chop up our water, right? So basically from 2 all the way to 10 here, we should chop it up. Maybe I shouldn't have drawn these blue parts above because there's no water above it. Okay, there you go. right? So from 2 to 10, which is where we see the water, yeah, we chop it all up. And then on a little slice, we compute what is the work that that slice will have to, uh, the work required for us to pump that slice all the way up, right? So let's think about that. Oops. Okay, so let's think about that. What is the work required for us to pump just that slice to the top of the tank? Right? So I'm going to call again each of these little points that we fix xi. And the work that we want to compute, let me write it this way. The work that we want to compute in the end will be we send the number of partitions to infinity, and then we sum I equals 1 to n, the work required just to pump that ith slice up, right? So let's try to write a formula for that. Okay. So that work, what is the work? Is going to be the force acting on the slice times the distance that it has to travel, right? So if this slice is, so there's a force factor and then there's a distance factor, right? Work will be force times distance, and the force in this case we just need to beat gravity, right? So at all times as we pump this slice of water up, gravity will try to pull it down. And so as long as we beat it, then we can compute the work required. We can, of course, use more work to push it faster up. But if we beat gravity, that's all the work required to do that, right? So the force of gravity will be the force acting on the slice at all times, which we can compute by using Newton's second law, right? So Newton's second law says a force is mass times acceleration. So we just need to compute the mass of this ith slice, right? This purple, you see this purple slice here. The mass times the acceleration of gravity, which is 9.8, right? So that's the gravitational force. The gravitational force in this case, let's see. Right, so the gravitational force in this case it should be negative because the motion is going up, right, and the force of gravity is going down. But we're gonna count it positively because the work done by the force of gravity will be negative, but we want to compute the force work required for us to pump. That's gonna be positive. Right? So mass times the acceleration of gravity, and the distance that it needs to travel is xi, right? So this slice that is at a position xi here has to travel xi to get to the top because the top is 0, right? So this is force times distance. Now to compute the mass of this slice, though, that's where it gets a little bit trickier. This slice is it's just a very short cylinder. So if you let me see if I can do something a little bit nicer. So I learned that I have this tool here that I should try to use. Right, so it's like a very short cylinder like that. And how can we compute the mass of this short purple cylinder that I drew here? Well, it's a cylinder, and what we can do is compute the volume of the cylinder and multiply that volume by the density of water, right? Because water has 1,000 kilos per meter cubic, so we can compute the volume here. If we compute the volume and multiply it by the density, we're going to get the mass in this slice, right? And to compute the volume, well, we've already discussed the volume of a cylinder like this. We just need the radius of the base and we need the height. Okay, so the height is delta x, is what we're calling delta x, the size of the partition that we made. Okay, and this radius here, let's call it Ri. So the radius of this cylindrical slice at xi. And we know that the volume of a cylinder will be, so the volume of this ith cylinder is going to be the area of the base, so pi times Ri squared, times the height, right? So if we, and then as I said here, if you want the mass, so this is the limit as n goes to infinity of the sum for all the cylinders. Now the mass is going to be the density, which is 10,000. Let me, not 10,000, just 1,000. So 10 cubed, that's 1,000. The density times the volume, right? So this is going to give you the mass times 9.8. That's the acceleration of gravity, xi. And this is equal to, let me scooch this over. This is equal to, okay, now I have a little bit more space. This is equal to the limit as n goes to infinity, sum of I equals 1 to n of, okay, so 10 cubed. Okay, so the VI is 10 cubed pi Ri squared times 9.8 times xi. I don't need that parenthesis, but I can keep it there if I want. 9.8. So the parentheses, okay, so it's 10 cubed times pi Ri squared times delta x, right? So that's the volume times 9.8 times xi. All right, so if you integrate, so if you take this limit, it turns into a Riemann sum. You see you have this sum, the number of partitions is growing to infinity, and this delta x is going to go to 0. This is going to turn into an integral. The x size, they start at 2 and they go all the way to 10, from 2 to 10. And then here you're going to get, well, 9.8 times 1,000. Let me just write 9.8 like that, right? Pi r of x squared times x, that's the xi, and the ri turns into this r of x dx, right? So that's the integral that's going to compute the work that we need, but we still need to figure out at the slice x, what is the radius of this circular slice, right? So let me draw, because then we're going to compute a formula here, and then we can compute this work. So let me draw the cone, but just from the side. Okay, and then let me draw the height. That's going to be important for us. And say now, so here's the x-axis. Say that we fix a certain value of x, and then you draw the slice, which is going to be a circle, but from this perspective, right? So if you slice with a plane here perpendicular to the x-axis, you get a purple circle, but from this perspective, it's just this purple line, and the radius of the purple circle is just this length right here, right? So this length. That's what we want to compute, r of x. We want a formula for it. Okay? And to compute a formula for r of x, what you have to do is look this triangle right here that I'm drawing in green. And if you look at this green triangle, it is inside of this bigger black triangle. And we can try to use triangle similarity to figure out what a formula for r of x, right? So in the big triangle, this length here, that's the radius of the base on the top, right? It's this radius here, which is 4 meters. And the height of the big triangle, so this number here, is the height of the whole cone, which is 10. Now, the base of the small triangle is the radius we need. And the height of the small triangle, maybe let me draw it over here. So how to compute the height. So you see how this is, so here is 0 in the x-axis, right on top. And this distance here is x, the value of x that we fixed, right? This is x. The whole thing is 10. So this green distance has to be 10 minus x, right? And if we use triangle similarity, we know that the height of the big triangle over the base of the big triangle has to be equal to the height of the small triangle over the base of the small triangle. Or if you want, you can write it in many ways, like the height of the big over the height of the small has to be equal to base of the big over base of the small is the same. There are many ways of writing it, but I would just say height of the big over base of the small, so 10. Height of the big over base of the big, so 10 over 4, has to be equal to height of the small over base of the small. So height of the small is 10 minus x. Base of the small is r of x. And so we can solve this equation for r of x. We get that r of x is equal to 4 times 10 minus x over 10. Okay, and so we can plug that into our integral. So this is an integral from 2 to 10, 9,800 pi. Now this squared, so it's going to be 4 squared is 16. 10 minus x squared over 10 is 100 times x dx. Let me start a new page to get a little bit more space. So I'm going to copy this. Okay, so this integral, let me cancel this 100 with that 9,800 there. And then pull some stuff out of the integral so we can integrate. So this 0, 0, we cancel with that 100. We're going to be left with 16 times 98 outside. I'll just leave it like that for now. So the work required will be 16 times 98 times integral from 2 to 10. I can take that pi as well. Pi 98, 16, and then integral from 2 to 10, x 10 minus x squared dx. Right, so these canceled. All right. Now we just need to solve this integral. You can just distribute this product here. 16 times 98 times pi. Integral from 2 to 10. Distribute this. So this is x times 100 minus 20x plus x squared dx. Let me compute this 16 times 98 because I think it's not going to simplify anything. 1568 pi. Okay, and then integral from 2 to 10 of 100x minus 20x squared plus x cubed dx. And the derivative is pretty easy to compute there. Okay, so here this turns into an x squared over 2. It will cancel with that 100, and it will be 50 x squared. Here will turn into x cubed over 3, and with that 20, nothing is going to help really. So 20 over 3 x cubed. And that will turn into an x to the 4 over 4. And we're going to plug in x equals 10, x equals 2. Okay, so here you can do some math, and then you see that the number you get, right, you plug in 10 squared, 10 cubed, and you subtract 2 squared. The number you get is 2048 over 3. That is 3,211,264 over 3 pi joules. That's the unit because we're in the metric system. Okay, well, unfortunately, the numbers in this problem are not very pretty, but hopefully the method is clear, right? So this one is a little bit complicated, so let me go through it again. So we wanted to compute the work required to pump all the water out of a tank to the top of the tank, right? So what we decided to do is take this, the water is from, we fixed this coordinate system, and our water was from x equals 2 to x equals 10. And then we divide it into small slices, small partitions, and we just computed, because different partitions will have to be displaced by different amounts, right? And that displacement will have a different amount of work necessary. So we focus on just one slice, and so we sum all the different works for all the different slices. And the work for one slice is going to be the force being acted on the slice times the displacement. If the slice is at coordinate xi, then the displacement is just xi here. And the force we use is the force of gravity, or since we're computing the work required, the force of gravity here will be negative because it's against the motion, but we're using positive to compute the work required to do this process. So it's just mass times acceleration, where we use the acceleration of gravity, right? So this is going to give us the opposite of the gravitational force. And so we need to compute, though, the mass of this slice, right? And the way we compute the mass of the slice is by using that we know the density of water, so we can compute instead the volume of the slice and multiply it by the density of water of 1,000. The volume times the density will give us the mass, right? So this is exactly the same thing, but the mass turns into this. To compute the volume of the slice, well, the slice is a cylinder, so it's the area, the circular area, times the height, which is delta x. So that's what turned VI turned into this. And then here, the sum, we turned it into an integral, right? So the number of partitions is going to infinity. The delta x is becoming smaller. We can write this as a Riemann sum. And then it turns into this. The 9.8 with the 10,000 turned into that. Pi Ri squared turned into pi Rx squared, where R of x is the radius of the slice at the variable x. It's going to be that circle, right? And the xi turns into x, the delta x turns into this dx. Right, so this is the integral formula for the work, which we need to compute, but we still need to figure out what is a formula for this radius of the slice at x. And so that's why we used this triangle similarity here, right? So the total height was 10, the length of the base was 4, the height of this smaller triangle is 10 minus x, and the base was r of x. We solved for r of x here, right? So we took this and we plugged it into r of x squared, and we got this term. 10 minus x squared, 16, and 100. Then we just kind of simplified some stuff, pulled some numbers out, solved the integral, and computed the work. The numbers were a little bit big, but It's just part of the process. All right. So in our Zoom meetings, we'll solve some more problems, and you can ask questions as well. But this finishes the section of work, which is, now I forget, but it might be 6.2 or 6.3. I forget. I apologize. All right. See you in the next one.